So what does the law of conservation of energy say? I've done my little lightning song and dance. The total energy of a closed system. By a closed system, what I mean is no outside sources of energy, Matt. Someone isn't allowed to walk into the picture and give something a push. Or you're not allowed to add some electricity to the picture. You're not allowed to add some extra energy to the picture. A closed system, the amount of energy is neither increased or decreased in any process. Instead, it remains constant. You can transform it from one type to another, but if you add up the amount of energy you start with and the amount of energy you end with, that stays the same in a closed system. The universe is a closed system, so a poetic way to say this is the total amount of energy in the universe remains constant. You can't get energy from nothing. You can only move it around, transfer it around. Mr. Dewick has a good demonstration for this. I do, behind me. I'll pause the video for a second. Let me give you a bit of a formal derivation of it. It says, according to the work energy theorem, if we have a closed system, no outside sources of energy, you get no useful work. What does that mean? So the work energy theorem, which you did add to your yellow formula sheet, said that work was the change in potential plus the change in kinetic, or the change in kinetic plus the change in potential. Michael and Priya, we actually added one equation to our yellow formula sheet. Ask your neighbors so you know which one you're allowed to add. Now that's the work energy theorem, the better definition of work. The more cumbersome definition of work. Force times distance is easier, but this handles more. But if it's a closed system, the amount of useful work you get is 0. And Matt, what's changing anything? No, what's changing anything? Say it right. So another way to think about this is to say 0 equals KE final minus KE initial and PE final minus PE initial. What does the law of conservation of energy say? It says you don't get useful work, you don't get extra energy out of a closed system. That's where the 0 came from. But do you notice now, Prith, if I take the two negative terms and I plus them to the other side, I get what I told you last year was the law of conservation of energy, G. I get the initials on one side and I get the finals on another side. I don't think I derived this equation with you folks in grade 11, but there's the more formal derivation of it. It says, you know what? You don't get free work, free energy from a closed system. Okay. I know that in fact, I have a colleague, he teaches the law of conservation of energy always starting from here. And there's some advantages because there's a 0 in the equation. Yeah, I always start from here. You may see sometimes in my answer keys when it says, write a work energy equation, it may start with something from here or from here. Usually I've gone and replaced it with one of these, but not always. If, Courtney, you had a question, or you? Okay. If we include friction, if we also say, hey, let's have some energy vanish as heat, it would look like this. KE initial plus PE initial equals KE final plus PE final. If the numbers don't balance, we get heat. A skate ramp. A skate ramp is a great example of this. Come here, Mr. Dewick. Physics 12. We have the energy skate park. Works better if it loads right away. Come on, computer. Really taking its time. Sorry for those of you on YouTube. So here's our energy skate park. If I want to, I can show you the energy. And Adrian, what you can see is the total energy stays constant, but we have energy transforming from potential to kinetic. At the bottom, we have maximum kinetic energy and minimum potential energy. Why isn't this 0? Not on the ground. The beautiful thing, because work and energy are a scalar, though, is if I want to, I can move the 0 height wherever I want. I can put the ground there mathematically, and now I can say, hey, it's all of the potential turning into all of the kinetic. I can put a 0 height wherever I want to. At the top, for a split second, all of my kinetic is turned into potential. But again, you'll notice the total remains constant because this is a closed system. Now, in real life, you can't do this. What bleeds energy away in real life? Friction. So we can turn friction on if I give a coefficient of friction just a little bit. Yep. You'll see now the thermal energy, the amount of energy that's being transformed into heat. Paolo, put your phone away. The thermal energy is going higher and higher, face down. And I'm having less and less energy to spare for potential height and kinetic speed. In fact, eventually, what will my final kinetic energy be? 0. What will my final potential energy be? 0. It'll all get dissipated as useless heat. But it's a nice example of the law of conservation of energy. And because energy is a scalar, it doesn't care about that curved path. Example 1, a projectile is launched straight up into the air. If it reaches a final height of 93 meters, what was its initial velocity? Use energy to solve this. Taylor, I could go VI equals question mark, A equals negative 9.8, D. I could solve this using kinematics in physics 11, but I can solve this using work and energy, using conservation of energy. My trigger is this. In this question, is there a change in height? Yes. Is there a change in speed? Yes. Then I start thinking maybe this is a job for conservation of energy. If there's a yucky, curvy path, it's absolutely a job for conservation of energy, like example 2 with roller coasters. But there doesn't have to be a yucky, curvy path. I can still use conservation of energy. So it does say to use energy to solve this. I'm going to say, okay, kinetic initial plus potential initial equals kinetic final plus potential final. The question doesn't mention friction or heat, so I'll ignore friction. I'll ignore heat. Are any of these 0? Are any of these 0? Sorry? At the top for a split second because it's vertical, I'll be at rest, sure. We're starting it on the ground. What's our initial height? And since it's MGH, yeah, PEI, it's not a real province. Oh, come on, really? Let's take this a bit further. This is going to be a half mv initial squared equals mgh final. Oh, what happens to the masses? Well, that's good because I didn't give you a mass. If I want to get the VI by itself, I think I would times by 2 to get rid of the 1/2. And that would give me a VI squared. How do I get rid of a squared? I end up with VI is going to be the square root of 2GH final. Before we crunch the numbers, if I had solved this with kinematics, I would have gone VF squared equals VI squared plus 2AD. I would have said VF is 0, so I would have had VI squared equals negative 2AD. To get rid of the squared, I would have square rooted. Here, I would have put in negative G, negative 9.8. Can you see I'm getting exactly the same expression with different letters, but I would have had D for the height. I would have put in a negative 9.8, which would take care of the negative 2 that ends up from kinematics. And it turns out I can solve this using a scalar equation. It's really the same thing. Which one's faster? They're about the same. It's going to be the square root of 2, 9.8, 93. How fast did it leave the ground at? 2 times 9.8 times 93. Why didn't I put a negative 9.8 here? energy is a scalar. I'm not going to include the negative 9.8 in this unit because that was a directional component. You get 42.7 meters per second. I'll be honest, John, I probably, unless the question ordered me to, wouldn't use work and energy to solve this question. I'd do it with kinematics. I'm pretty good at that. But John, roller coasters. I like roller coasters. I like roller coasters. I like roller coasters. Roller coasters are a nice question. Example 2, John says, a roller coaster car is traveling at 22 meters per second. If the car starts out at a height of 12 meters, how fast will it be traveling when it gets to ground level? John, is there a change in height in this question? Is there a change in speed in this question? If we looked at the roller coaster from the side, would there be a yucky, curvy path? That's a job for conservation of energy. And the beautiful thing, because conservation of energy is a scalar, John, it doesn't care if the roller coaster looks like I just sketched, or if the roller coaster does this, or if the roller coaster does this. Doesn't matter. All it cares about is where you started and where you ended. This is a job for the conservation of energy. G. KE initial plus PE initial equals KE final plus PE final. John, does this question mention heat or friction? Oh, no, it says ignore friction. If it did not, if it said include heat, I could. We will later. By the way, when I find the speed at the bottom, will it be bigger, smaller, or the same size as 22 meters per second? When you get to the bottom of the roller coaster, are you going faster or slower? So, am I looking for an answer bigger, smaller, or the same size as 22 meters per second? Built-in error check. I know I'm going to be going faster at the bottom. If I accidentally include a negative somewhere that I shouldn't, and I get a smaller answer, I know I'll have messed up. Yes? Are any of these 0? PE final? Okay. A half mv initial squared plus mgh initial equals a half mv final squared. Oh! What else do you notice? The m's cancel? John, have you been on a roller coaster before? When you got on the roller coaster, before you got on, did they make you step on a scale? Did they weigh your mass to carefully balance everything out? Do you know why? Masses cancel. Or let me ask you this. Can an empty roller coaster car make it through the same way a roller coaster car full of fat people could make it through? Yeah. Now, in real life, don't write this down, there would be friction, energy lost to heat in real life. Which means in real life, the masses technically don't cancel. But if we grease our roller coaster down and get that number as small as possible, it's almost negligible so that you have a really wide safety margin for the masses that can make it through this without any trouble. Maybe in 50 years, the way the US is going, maybe then the people might be so heavy that it won't make it through and the car might get stuck. But for now, we're going to assume the masses cancel. Is that okay? John, what am I trying to find? VF right there. I'm going to do another thing. You guys can probably handle this. What's right in front of the VF? And what's in front of the M? I'm going to go times by 2, times by 2, times by 2. Have I multiplied everything by 2? Yes, so this is legal. By the way, kids that use this shortcut, some of them forget to multiply this middle term by 2. I multiply everything by 2, but when I do that, that 2 and that 1 half cancel, that 2 and that 1 half cancel. In fact, what I get is this. VI squared plus 2GHI equals VF squared. Psst, don't write this next bit down, just look up Taylor. This might look really similar to VI squared plus 2AD equals VF squared. In fact, that is really where the equation comes from. I think I derived it with you this year. I know I never derived this equation in Physics 11 because it's a bit of a pain. It pops out of energy almost intuitively. John, you agree with me how to get rid of a squared? Okay. How fast are we going at the bottom of the hill? It's going to be 12 squared plus 2, not negative, just 9.8, times, not 12 squared, Mr. Dewick, I read the wrong thing, 22 squared, right? 22 squared, sheesh. The height is 12. Don't make that mistake. 22 squared plus 2 times 9.8 times 12 square root. Get 26.8. How fast is that? Well, if I times by 3.6, it's almost 100 kilometers per hour. You go pretty fast. This would be a, C plus B, maybe even a B minus level thrill ride. Not going crazy fast. I've been on roller coasters that go faster, but 100 with the top down on a roller coaster would get your attention. Be fun. By the way, what if accidentally I'd put in a negative for the 9.8? This is why I said I kind of like to know ahead of time. When I square rooted now, I'd get an answer slower than that 22, and I already told you, I know I'm going faster at the bottom, so built-in error check. Okay. Now turn the page. I don't know if I'm going to make it. Time for a cough candy. An object is dropped from a height of 40 meters, strikes the ground at 25 meters per second. How much heat energy was produced during the fall? Is there heat energy produced? Yeah, if you actually ignore air resistance and you run the numbers, you'll find it should hit the ground faster than 25. So we're saying we actually did the experiment. It hit the ground at 25. You know what? We must have lost some energy to air friction, to air resistance. We heated up the air a little bit. How much? Courtney, in this question, is there a change in height? Is there a change in speed? Is there a yucky, curvy path? No, but is it talking about heat energy? Yeah, this is a job for conservation of energy. So, I'm going to start out going KE initial plus PE initial equals KE final plus PE final, but this time, Courtney, I guess I have to add some heat. Got to bring the heat. Hey, folks, are any of these 0? Sorry? PE final? Oh, if we drop something, I taught you last year, anytime I use the word dropped, we'll assume our initial velocity is 0. We'll assume we're holding it still and then letting it go. So we can do that. And I'm trying to find the heat. How would I get the heat by itself? What do I do with the KE final? Sorry? Minus it. For some reason, Kareem, on this question, a lot of kids for some reason divide it over, and I never understood why, but it happens. Don't. So I'm going to get this, mgh initial minus a half m v final squared equals heat. Do the masses cancel this time? No, because there's not a mass in heat. Okay. I'll do heat in red, just because that's a heat color, equals 18 times 9.8, not negative because we're in Scalarville, 40 plus, Mr. Duke, minus a half, 18, it hits the ground at 25 squared. How much energy do we lose to heat? Oh. $18 times 9.8 times 40 minus 0.5 times 18 times 25 squared. Do you get 1431? I'll go to 3 sig figs. I'll go 1430 joules. Is that all right? Let's take it a bit further here. Hedrick, what's example 4 want me to find? Third word. Yeah, don't overcomplicate it. How much what? Work. Don't write this down, but here's what my brain thinks. My brain says, well, work equals force times distance. Hedrick, do you see a force or a distance mentioned in this question anywhere? No. So, work is also the area under a force versus distance graph. Did they give you a graph? Okay. Then, I'm going to use the work energy theorem, the third definition of work, the one that we added to our formula sheet, which is change in potential plus change in kinetic, or change in kinetic plus change in potential. Hedrick, does this question imply a change in height at all? I think I'm going to assume that's 0. Level road. Okay. Matt, what's changing anything? So this is going to be KE final minus KE initial. It's going to be a half MV final squared minus a half MV initial squared. 0.5, 1200. Hedrick, what's our final speed?
50 kilometers per hour.
Did you say kilometers per hour? Let's do a conversion. I'm so lazy, I'm just going to go 50 divided by 3.6 all squared. I'll just do it all in my calculator because I know it's divided by 3.6. I could have done it on separate lines, but why bother? Minus 0.5 times 1200. My initial speed is 80 kilometers per hour, so I'll divide that by 3.6. How much work is done? You should find something a little weird on your calculator as the answer. What? Negative? What's the negative telling me here? If the car was traveling east, what direction did the force act? West. If the car was traveling forward, what direction did the force act? Backward. There's our generic one. Or another way to think about it is the car has to lose energy. The car has to lose energy. How much energy? 1.81 times 10 to the 5th joules. If you left the negative off, I would probably give you full marks, except not if you left the point off. Let's try that again. Because really it's an energy loss. The negative is just telling you it's an energy loss. It's not a directional component per se. It comes out of the fact that force is a vector and has a direction opposite. But if you just said, how much work does it take? It takes 181,000 joules of energy. Sure, because that energy doesn't vanish. What force does the work? What force brings your cars to a stop? Friction. Brakes does the work. Where do you think the energy is transferred to? Yeah. Except in hybrids, hybrid vehicles. So in the hybrid vehicles, the way they have some of them set up, the Prius I know has it, the Tesla has it, I know the Chevy Bolt has it. I'm not sure which of the other ones do. They have something called regenerative braking. So when you hit the brakes, when you want to slow down, rather than your brakes taking this energy away into heat. Instead, the system bleeds off your kinetic energy and turns it into electrical energy and uses it to recharge the batteries. You're still bleeding off the energy, so you have to slow down. But rather than wearing your brakes out, we actually use the kinetic energy to recharge the batteries. A couple of summers ago, I took a Tesla for a test drive. They are nice. They really are rainbows and unicorn dreams. They are just wow. And one of the things, so the way the Tesla works is when you put your foot on the go pedal, they don't call it a gas pedal because there's no gas. When you take your foot off the go pedal, it feels like you're hitting the brakes right away. You're not. Because the regenerative braking kicks in right away, and so right away you feel yourself slowing down, decelerating, because it's bleeding off the energy. In fact, I asked the guy with me, I said, I'm hardly ever actually hitting the brakes. I'm only hitting the brakes at the very, very end to come to a complete stop. He said, yeah. I said, I think the brakes would last a lot longer. He said, yeah, we tell people check your brakes every 10 years or so. Oh, kind of nice. Someone last class asked me, Mr. Duick, does that mean if you had a Tesla on the top of a hill and its battery was totally dead, could you recharge the batteries by rolling it down the hill? So we went in our magic physics world. I said, well, if you had an infinite hill, you could recharge it all the way. It would eventually hit terminal velocity, but it would still have kinetic energy. You could still keep bleeding it off, yeah. But it's not free energy. You would have had to, the tow truck or the person or the crane, whoever lifted it to the top of the hill, had to supply that energy to begin with, right? It's not free energy. But instead of having it go to heat, want to have it go to something useful. Let's put everything kind of together here. An object is pushed across a level floor with a coefficient of friction for a distance of 6.4 meters by an applied force of 58 newtons. Okay. Priya, my joy, what does A want me to find? Done by the. So I'm going to write work applied. My first thought is to try force times distance. You know what? They gave me a force and a distance, so I think I am going to go the work done by the applied force is going to be F applied times distance. And I think they're in the same direction. Let's suppose the applied force is Dylan pushing. How much energy, how much work does Dylan contribute to this system? Well, it's going to be 58 times 6.4. $371.2 joules. Normally I'd round off to 3 sig figs, but I'll keep this whole thing just to walk through the whole example. So Dylan gave up that many joules of energy to this system. Did that all go into making this object speed up? No. B asks, what's the work done by friction? Well, the work done by friction is going to be the force of friction times distance, where the distance is going to be 6.4 meters, however long you're pushing it. Friction is what times what? Oh, you know what? I think we need a good free body diagram. How about over here? I think we're going to have mg down, normal force up. Here's Dylan pushing. There's friction slowing. So, Prith, you said mu times the normal force. I don't know the normal force. Oh, but look. I know another force. And in this case, we're on flat ground, and it's not a lawnmower question where the force is at an angle, so I can say, hey, it's going to be mg. And D, it's going to be mu 0.35, m 12.5, G 9.8, D 6.4. And I get 274.4, which is wrong, technically. Why is this wrong, technically? paused. You'll see it. Why is this wrong technically? Ethan. Really, because the force and the distance are in the opposite direction, if we brought in that cosine of theta definition, theta is 180 degrees, we could call it negative. Now, if you didn't put the negative there, I'd mark you correct as long as you thought it the right way in part C. Ethan, what's part C asking me to find?
What is the network?
The network that's done is the amount of energy that Dylan poured in minus what we lost to friction. Or if you went plus negative. If you called friction negative, then it would be plus negative. Or if you called it positive, but then you said it's an energy loss, and so I'll subtract it in this equation. Just don't go minus minus. How much energy actually went into making the object speed up? Only 96.8 joules of your 371.2 joules of work went into making this object speed up. The rest went into heating up the floor. If we assume the object started from rest, what will the final speed be? Well, we know the total amount of work. We can now bring in the work energy theorem. We can say work is also the change in potential plus change in kinetic. And Dylan, I'm going to argue I don't think there's any change in potential. It does say level ground. Okay. Why did I bring this in? Because Courtney, they wanted me to find final speed. I just found work, and this has speed in it. So now I've got them in the same equation. This is going to end up being work equals KE final minus KE initial. Which one of these is 0? It does say started from rest. So 0. Running out of room here. I don't know why I only left one line, but I did. That was dumb of me. You're going to get this. 96.8 equals a half mv final squared. Dylan, my friend, how would I get the v final by itself? What would I do with the 2? Times it and then divide by, and then how to get rid of a squared? Can we do that in one step because I'm running out of room foolishly? VF is going to be 2 times 12.5, times 96.8 divided by 12.5 square root. Two times 96.8 divided by 12.5 equals square root 3.94. There's another way we could have done this. If I had just given you the situation and I'd said, find the final speed, I'd only asked part D. You could have gone winner minus loser equals MA, F applied minus friction equals MA, divide by M. You could have found the acceleration. VI is 0, D is 6.4, and you could have found V final by going VF squared equals VI squared plus 2. You get the same answer. Sometimes one method is faster than the other method, but you'll also notice you'll get a lot of the same numbers or operations appearing along the way to converge on the same answer. So I'm not going to do E. We could. We would go winner minus loser, find the acceleration. Once you have the acceleration, D is 6.4, VI is 0, find VF. Hey, we get to vote. So sit up, shape up, think up. It says this. 3 projectiles, A, B, and C, identical projectiles, are fired from the same machine with the same velocity. So everything about these is identical. Oh, and let's fire them on the moon so there's no air resistance to worry about. Their paths are labeled A, B, and C. So they have the same mass, they have the same VI. We just have them at different angles. At location 1, which it looks like it's at the top of each path, which projectile will have the greatest kinetic energy? A, B, C, or all the same? At location 1, which projectile will have the greatest kinetic energy? A, B, C, or all the same? Once again, you're going to vote. Once again, how high you hold your hand up is how sure you are of the answer. I'm positive. I'm pretty sure. I'm only voting because Mr. Duke will make fun of me, and he will. Who says A, Mr. Duke? A, because it's the highest. A, because it's the highest. No one. Who says B, Mr. Duke? B, because it's split in the middle. You have the most kinetic energy because you're not splitting as much. B. No one. Who says C, Mr. Duke? C. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Who says D? Well, you got to vote for something. Okay. Convince me. Convince me. What's the correct answer, and convince me? No one. Do they all three have the same amount of energy to start? Everybody say yes. Okay. And at the beginning, it's all kinetic. Okay. So they have this much total energy, and at the beginning, it's all kinetic. I'm doing the skate park little bar graph now. As the height increases, what happens to the kinetic energy? So, what if I only have a tiny little bit of height? I'll only have lost maybe that much. I'll still have this. Which one of them has the smallest amount of height? Right? On the ground, it's all kinetic. The higher you go, the less kinetic, the more potential you'll have. Now, my last class got into an argument because they argued that your velocity is 0 at the top of each one. Why were they wrong? Your vertical speed is 0, but your horizontal velocity, you still have a lot of kinetic energy. Okay? So, defend your answer from law of conservation of energy from the loco rule. Smallest PE means biggest KE. Smallest potential energy, smallest height, means you got more kinetic energy. Pause the video. Okay. All right, part B. At the 3 points marked 1, which projectile will have the greatest total energy? A, B, C, or all equal? What's the answer here? All equal, because they all started out with the same amount of energy. In fact, anywhere on the path, the total energy for all of them will be identical. Some more of it may be kinetic, some more of it may be potential, but if you add it all up, it'll be the same total as they started with. Using principles of physics, from law of conservation of energy, total E is constant everywhere. Heck, let's even add the word everywhere, and then I think I just answered C. At the point marked 2, which projectile will have the greatest total energy? Because they're all the same height. Total, well, even if they weren't the same height, total energy would be the same everywhere. Okay. Using principles of physics, explain your answer. I just did. we go till, okay, let's go like this. I'm going to pause here. If you want a little start, now I am going to add more questions to this. I haven't done the Tarzan vine. I'll say you can try it, but I'm going to talk about that next class. 2 is good. Skip 3. 4 is good. Skip 5. 6 is good. Actually, no, I'm going to include 5. Ha, fooled you. 7 is good. 8, 9, 10. I'll give you, next class, I'll finish off the lesson. I'll start the next lesson, but I'll give you about 20 minutes at the end of class to get this stuff done. Okay?